Welcome back to ECE 442-542. Hopefully you had a relaxing break or at least an energizing break of some kind. I'm bringing you back to reality. Exam number 3 is April 12th. So just to get you thinking about our next exam. Homework number 5, I'm going to wait just a little bit of time before I make that available, but that will be coming soon. I want to make sure that we've covered a fair amount of material before I hand that out, and then you're going, how do I work these problems? What I want to do today is basically remind ourselves where we've been. Basically, what was the material that we covered in exams 1 and 2, and that will, I hope, get us back to thinking about digital control, which is what this class is covering. And then we'll look at where we are going, which is now we can get into designing controllers. And how do we do that? Well, before we even get into controller design, we still have to worry about connecting performance specifications to S-domain pole locations and consequently Z-domain. So I hope, maybe not today, but the next time, you will be seeing circles, hearts, and wedges, geometric shapes, and those correspond to particular types of transient performance specifications. So if you're thinking about circles, that might be consistent with settling time. If you're thinking about hearts, I know this is maybe a month late. We should have done this on Valentine's Day. But hearts are like percent overshoot, and will have logarithmic spirals that sort of resemble hearts on their side, not necessarily upright, but they are somewhat heart-shaped. And then we will be dealing with angles, which are more connected with peak time, or how fast our system responds. And we want to do that, understand these connections, so that we can actually generate desired transfer functions. Where do we want our poles now that we know how these systems might behave based on the material that we've already learned? Maybe we want to modify that performance or that behavior of the system. I'm not sure you'll be able to write all of these down as we scroll through them, but where have we been? We've been through quite a journey, although it doesn't seem like it's been that long, but we talked about difference equations in the time domain, what happens when we transform those. We get into the Z domain or the frequency domain. We now can look at transfer functions. We've looked at solutions to difference equations, be that homogeneous or unforced, or initial condition responses. What happens when we force that behavior? We can solve those. The sample period, how do we select that? And we have this rule of thumb, which is 30 times the highest frequency. And that point was maybe missed a little bit on exam number 2. But you're looking for the highest frequency, and then based on that, you want to sample 30 times that highest frequency. We've talked about the Z-transform, mapping. Oh, I guess now it's time for you to respond. What is the Z-transform? Have we forgotten that? The formula? If I now say capital X of Z, what's the expression for the Z-transform? Is it an integral? Hopefully you remember it's at least a summation. And let's say that the time index is little n. And if it's now the generic or the most general form of the Z-transform, what's the lower index that we're summing with respect to? We're going way over to minus infinity. And we go all the way to plus infinity. And we now weight that time sequence of values, little x of n, by this complex variable raised to the minus n power. And z to the minus 1 is like a delay. And now we are weighting these time domain sequence values, little x of n, by delays in a sense, and that now produces this Z transform. Audience participation again. What's the mapping that we've used to go from the S-plane to the Z-plane? What's the connection between S and Z? I just maybe gave it away. I said Z to the minus 1 represents a 1 sample period delay. What does that look like, or what's an advance in the S domain look like? If I said, now what is Z equal to in terms of a function of S? You're playing with me, I assume. This is now e to the st, right? So our mapping was Z is equal to e to the st. And you've learned how to inverse Z transform. The basic way is to do the pair comparison in a table, and so we now do some partial fraction expansion. What that inverse Z transform looks like to make it unique depends on the region of convergence, and we really only have 3 different regions of convergences, and I've indicated those here, but the one on the left represents what kind, and now I want you to answer as a class with thumbs. So if it's an up thumb, that means it's causal. If it's a down thumb, it's non-causal or anti-causal, the sequence that corresponds to from these pictures. And if it's two-sided, then you can show me a horizontal thumb. So for the leftmost picture, here's the poles of that system, and now don't give it away yet. I want you to now, with your thumb somewhere close to your body, either show me up for causal, down for non-causal, and horizontal for two-sided. At the count of 3. Left picture for that region of convergence. 1, 2, 3. Okay, we should be wrestling with thumbs, apparently. We're still on break. But this is now our causal behavior, or non-negative indices. For the middle region of convergence, what do you have at the count of 3? Causal, non-causal, or two-sided? 1, 2, 3. Okay, I hope that's not in, never mind, I won't. But yes, it's non-causal. And the last one, by process of elimination, since it's annular or bagel or donut shaped, this is two-sided. Now, relative to the behavior of those sequences, can we tell anything from these diagrams if they are bounded sequences or not? We have to be told a little bit more information, don't we? We have to know, where do these poles live relative to the unit circle? And does the unit circle, and here I think we've made, it's a challenge to try to word this or phrase this, but the unit circle now needs to be contained within the region of convergence for that to be a bounded sequence. And some people were interpreting that to mean, oh, as long as the region of convergence sort of encloses the unit circle, that was within. But we want there to be overlap between the unit circle and the region of convergence. They have to overlap if they are now, if the unit circle is contained within the region of convergence. We've also gone through discrete equivalents, both in the time domain and the frequency domain, where we had state, space, and transfer functions. If we were doing the transform zero-order hold equivalent, then we have this pre-multiplication by 1 minus z to the minus 1 and the z transform of g of s over s. Or if we're doing it exactly in the state space form, we now need to find the system matrix A and find its exponential, matrix exponential, e to the at. That's now our state matrix or system matrix in the discrete time setting. And the input matrix gamma is this integral, e to the a mu b d mu. We could also do numerical integration in state space or frequency domain, and that's just replacing S with a particular Z domain expression. We could do the forward, the backward, or the trapezoidal. And we've talked about pole zero mapping, and we worried about zeros at infinity, determined by if we needed to ensure that one delay was actually present in the implementation. Then we might not map all of our zeros at infinity to factors of z plus 1 in the numerator of our pole zero mapping relationship. That's where we've been. Where are we going? What we want to do now is focus on creating or realizing or coming up with these controllers, transfer functions, let's say capital C of Z, in our generic block diagram. We want to be able to design those, and I might call that a controller, I might call it a compensator, but now what we want to do is focus on this particular part of this block diagram, and that's to do what? That's to try to change the behavior. Maybe our behavior's poles are not where we want them to be for transient reasons. Maybe we want a particular steady state error behavior, and so that may induce some kind of poles at z equal to 1 in our controller, capital C of Z. What we are doing now is, you could think of, we're interested in what's in this shaded region. And we could now say this, that's maybe difficult to read, so let me, that's now some transfer function between the reference input R and the output Y, or we could now say, oh, this is what we're actually trying to achieve. We're trying to come up with some desired closed loop behavior, and now what we want to do is try to develop insight into that process. How do we specify what it is that we want? What do we want T sub C of Z to be when T sub C of Z is actually coming from this interconnected structure in a closed loop control scenario? How do we now come up with a desired T sub C of Z? Or, if we're worried about the transient, what performance is needed? Or we may want steady state accuracy. We may want zero error between where we want the output to be and where it actually is. Or maybe we can tolerate some steady state error, but we want to improve or enhance our transient behavior. For that reason, we need to get very comfortable with performance specs or specifications that we want our system to achieve, and we've talked a little bit about that relative to second-order underdamped systems. Here is our S-plane and our transfer function connecting to the S-plane. I simply have two poles that are indicated by X's, one in the second quadrant, one in the third quadrant, and those poles are moving around in the complex S-plane based on these parameters. The zeta parameter, the damping ratio, the natural frequency is the distance that those poles are from the origin. The damped frequency is the vertical distance from the real axis. The damping sigma, which is the damping ratio times omega sub n, is the distance into the complex S-plane in the horizontal direction. And I might now call that S equal to minus sigma plus j omega sub d, or I may break it up and parameterize it in terms of zeta, the damping ratio, and the natural frequency, omega sub n. And what we want to do is make those connections relative to not only or understanding those in the S-plane, but eventually mapping these through our S-plane to Z-plane mapping into the Z-plane, so that we now start to understand circles, hearts, and wedges relative to these performance specifications. And here is our terminology. We have the damping, that's the distance into the left half plane. We have our damping ratio, which is the real part of those poles divided by, or the ratio between the real part and the hypotenuse, or the magnitude of S is in the denominator and the real part of S is in the numerator. The magnitude, the distance away from the origin, is our natural frequency, and that could be with zeta equal to 0, where we have a pure oscillation and no damping, or when zeta is equal to 1, when we have now two real equal poles at minus omega sub n, and no complex or imaginary component. And we also can identify the damped frequency, and it's damped meaning it's some ratio or some fraction of the natural frequency omega sub n. Those are the terms that we will be using, and we will connect these S-domain poles with step response behavior. And this is now connecting us with our transient performance in the continuous time setting. And there's several different points to be identified in this second order underdamped system response. We have when the time that response initially maxes out, or the peak time, T sub P, or the maximum value of the output Y. We have the final value where it eventually goes. So apparently the posters do not take a break. We have our poster hammer going, and it's just right on time. Nothing but consistent for that. I think I could write a good recommendation letter for that particular person. We have peak time, T sub P. We have the maximum value of the output which occurs at that peak time, and we will see a little bit later why in this class it might be more or easier to talk about a 1% settling time than a 2% settling time. It just makes some of our formulas a little cleaner to talk about a 1%. But a 1% settling time is now consistent with 5 time constants. And that's the time that the response gets inside this 1% tube around the final value, and it stays there. Obviously, it gets in that 1% tube many, many times, but it waits a while until it gets in there and stays in there and doesn't leave or exit that 1% tube. When that first happens, that's what we call our settling time. Question? Yes, so we haven't really derived 5 time constants maybe in this class, but if you look at e to the minus, let's say, t over tau, and now if you look at e to the, if at a time t equal to 5 time constants, you have 5 tau over tau, or that's now e to the minus 5. And if you look at e to the minus 5, it's going to be a little bit less than 0.01. And that's where our 1% comes from. That's the settling time that we've agreed to use in this class. And what we want to do now is connect those time domain characteristics or properties, peak time, settling time, and percent overshoot. You can see that we also, depending on the relationship between the maximum value of the output and the final value, that will give us a percent overshoot behavior. We want to now relate those to locations in the complex S-plane. And the first performance specification that we will talk about is this 1% settling time. T settle, which is related to the distance we are into the left half plane, and that's determined by our sigma value. And if we now say we have 5 tau, well, tau is inversely related to the sigma, or the damping, or the settling time is now 5 over sigma, or the real part of our complex poles. We can solve that for sigma. If somebody gives us a settling time and they say, produce a settling time, a 1% settling time of this amount, we would divide that value in seconds into 5, and that tells us how far our dominant real part of our poles needs to be. In this particular diagram, I hope it's clear. Well, which of these sigmas, if I say sigma 2 produces a blank system response, then sigma 1. If I had dominant poles that had a real part associated with sigma 1, or they had a real part associated with sigma sub 2, which of those pole pairs gives me a smaller settling time, or a faster settling system? Sigma sub 2 produces a, and here you have two options, slower or faster system response than sigma 1. Are the red poles faster than the black poles? What's an up thumb mean? Yes or no? I've seen thumbs up, I've seen thumbs down, and I'm not asking causal or non-causal. Now I want to know yes for a thumbs up and no for a thumbs down. So now what do I want to do? I need to remember how I phrase that. Or sigma sub 2 produces a faster system response than sigma 1. Now I've changed the question. Is that true or false? Up or down? 1, 2, 3. And now I have some people that have crossed their fingers. Sigma sub 2 is further into the left half plane. It's further away from the origin. That gives you a bigger sigma. So if you put a big sigma underneath 5, that's going to make T smaller. So it'll be a faster settling time. Sigma sub 2 produces a faster system response than sigma sub 1. And the takeaway that I want you to remember is that if somebody starts talking about settling time, you need to think in terms of vertical lines, or distance away from the imaginary axis, sigmas. That's in the continuous time case, and we'll eventually show where that connects in the z-plane. Percent overshoot. And I tried to color code this. Obviously, I needed something to do. But the final value of the output was red in the transient response. And some people get that confused. Where do I put y max and where do I put y final value? Well, the final value goes in the denominator, and you want that difference between the maximum and the final value, and that divided by y final value gives us the percent overshoot when scaled by 100%. Or if you relate that to the time domain expression and find the percent overshoot formula in terms of zeta and omega sub n, actually it's just a function of zeta. The percent overshoot is 100 e to the minus zeta pi over the square root of 1 minus zeta squared. And I'm sure you're all going to want to run home and try to now solve that equation for zeta, and that will now give you this nice expression that you've probably memorized if you've had an earlier class. You now have natural log of PO over 100. PO is in percent. If you had a 20% overshoot, you would now have 20 for PO divided by 100. Then you divide that by pi squared, and I'm assuming that you all enjoyed Pi Day over spring break. I had to go get a pie or have someone else give me a pie. What? No. No, it wasn't. No, it was late in the evening on Pi Day. So it wasn't 3.14 at 1:59. That's what I had a student tell me he got married on Pi Day at 1:59 p.m. He said he convinced his wife that that's when they had to get married. Later on, I think after I'd awarded grades, he reneged that and said, "Oh, I really was just playing with you, Dr. Tharp." I said, "Oh, I enjoyed that story." But here we are back to pi squared. Pi squared is what, roughly? If you don't have a calculator, what would you plug in for pi squared? 10. It's almost 10. So if you need pi squared, if somebody says pi squared, you're just thinking 10. Okay? It's not quite a perfect 10, but it's close to a 10. Then you can relate zeta and percent overshoot with this curve, where a nice zeta value gives you a 5% overshoot, and that nice zeta value is 0.7. Where now the zeta value, and I guess I will do it in just a minute, but I will relate that to the angle in the S-plane of those complex poles. But here you can see different connections between zeta values and percent overshoot, or if you don't like these approximations, you can start plugging those values into your calculator and get a particular value for zeta based on the percent overshoot. This now connects or relates the percent overshoot. Suppose I have the same natural frequency of these two poles. I have two pole pairs, and I have their twin down in the bottom half of this complex S-plane. But now they are the same distance away from the origin. They've just been rotated. One has an angle of theta sub 1. One has an angle of theta sub 2. And do you remember which has a larger zeta value, or where is zeta equal to 0? Do you remember? What is zeta? Zeta is the damping ratio. So if you have no damping, zeta would be 0. Where would you not have any damping with your poles? Right on the imaginary axis would be where, so it's on the vertical axis is when zeta is equal to 0. When zeta is equal to 1, it's all the way down and you have real value. So here, if you were up here, this would be zeta equals 0, and if you were down here, this would be zeta equal 1, and they swing around. If you keep them the same distance away from the origin, if your natural frequency stays the same, they don't change their distance away from the origin, but they do rotate around from no damping, zeta equals 0 when they're on the imaginary axis. That's when they just sit there and shake, and they don't damp. And then when they come and they have critical damping, or when you have two real equal poles with zeta equal to 1. Now, if this is the case, if you wanted to have less overshoot, less percent overshoot, I want you to start connecting these angles or these wedges in the S-plane. How do you want your edge to be moving? For example, in this case, if you look at theta and zeta, here's zeta. Well, if I said cosine of theta, that's now the adjacent over the hypotenuse, or cosine of theta is now zeta. So you can relate theta to zeta, or theta is now the inverse cosine of zeta. And we said that a nice value of zeta is 0.7, and if I now do the inverse cosine of 0.7, or what angle theta has a cosine of 0.7? You remember? That's a theta of 45 degrees, isn't it? So this zeta of 0.7 now gives you an angle 45 degrees, or a 5% overshoot. And what I want you to be thinking now is, if somebody says percent overshoot, I want you to be thinking zeta. And now we could do the same question. Theta sub 2 produces more or less overshoot than theta 1. So now theta 1 is a bigger angle than theta 2, so you have a bigger wedge of pie or pizza. Yes, I'll put talking food. But we now have a wedge. Theta 1 is bigger than theta 2. Theta 2 produces more, thumbs up, less, thumbs down. 1, 2, 3. Theta 2 now has more damping. The pole has now moved further into the left half plane. It has a bigger real part. Its angle is smaller, so that now we have a smaller angle. If you said theta 1 is 60 degrees, what's its cosine? 0.5. What's the cosine of 45? 0.7. So we have more damping with theta sub 2. So theta sub 2 produces, what did I ask? Less or more overshoot? Theta 2 produces, I hope we said less. Is that what you were saying? Did you have a thumbs down on that? The poles associated with theta sub 2, and if you were thinking of this, now if you wanted to decrease the percent overshoot, then you want your zeta to be going more towards the 1 value than to the 0 value. And I hope that's clear. So now we've looked at vertical lines, we've looked at angles. Now we're going to talk about peak time, and this now involves horizontal lines. The time to peak, if we derive that relationship, is pi over omega sub d. And omega sub d is just the distance those poles are away from the real axis in the S-plane. In this case, I'm wanting you to connect t sub p, time to peak, with omega sub d. And I hope it's clear that if omega sub d gets bigger, omega sub d sub 2 is bigger than omega sub d sub 1, which of those poles peaks quicker? The one in red or the one in green? So here the question is, omega sub d sub 2 produces a slower or faster system than omega sub d1, or t sub p sub 2 is something relative to t sub p sub 1. So thumbs up if omega sub d produces a, how do I want to phrase this? Faster. So omega sub d sub 2, if it's faster, thumbs up. If it's slower, thumbs down. 1, 2, 3. So omega sub d sub 2 is bigger than omega sub d sub 1. We divide pi by a bigger number, and what's t sub p do? It shrinks. The time to peak gets smaller. That means our system is moving faster. Did I scare you? Maybe you'll never forget time to peak. Have to be quick. So omega sub d sub 2 produces a faster system than omega sub d sub 1. Now what we want to do is translate these vertical lines, horizontal lines, and angles into geometric shapes in the z-plane. They're not going to be the same because of our mapping. Our mapping is z is equal to e to the st. So let's now use that. We now know that z is equal to e to the st. And if we parameterize s in terms of the damping ratio and the natural frequency, we can now say, oh, z is equal to e to the, let's say s is minus sigma plus j omega sub d times t, or that's now e to the minus, well, let me put the s inside parentheses, sigma is now zeta omega sub n, plus an omega sub d, that's j, omega sub d is omega sub n square root of 1 minus zeta squared, that's the damp frequency times t, where this is now our sigma value, and this is our damp frequency omega sub d. If we distribute that t inside the exponent, and separate those exponents into two pieces, which we can do if we're adding exponents. We can now factor that into two different parts. We can now say, oh, z, we can write as e to the minus zeta omega sub n t. Again, this is our sigma value, times e to the j. And now what I want to do is actually push that t in between omega sub n and the square root of 1 minus zeta squared, just because it's easier to talk about omega sub n t. I haven't changed its value at all, but now we have omega sub n t square root of 1 minus zeta squared, where the combination of this and that is our omega sub d. What I want you to start to see, though, is what's happening with this parameterized form of z. E to the minus sigma t, that's really just the radius away from the origin in the z-plane. And what's this e to the j? That's e to the j some number. That's like e to the j at an angle. E to the j theta sub d. So that now we have, this is r, and we have e to the j omega sub dt, or if we just collapse omega sub dt into an angle, we now will say, oh, that's r at an angle theta sub d, where this omega sub dt is what we will call theta sub d, so that in the z-plane, when we start talking about complex poles in the z-plane, what we will be doing is now we are talking about two poles in the first quadrant and the fourth quadrant. They are a distance away from the origin of value r, and they are at an angle of theta sub d. This location right here is z is equal to r e to the j theta sub d. Or you could think of this real piece being r cosine of theta sub d, And you've seen that appearing throughout different z transform expressions. And the imaginary component is now r sine of theta sub d. And I hope it's clear that that theta is not the same as what we had in our theta angle in the s-plane. And if I wanted to, I could say, oh, this is now my x distance, x bar, and maybe this is my y component, y bar. Now what we want to do is we want to translate these performance specifications, settling time, percent overshoot, and peak time, into different shapes in the z-plane. They will no longer be vertical lines, horizontal lines. Well, we will have some angles or wedges. So let's start by looking at, relative to that, and I hope it's clear now when somebody says, oh, where are my complex poles? If you think about what happens in the s-plane, you should be able to immediately translate those into the z-plane locations that they belong in, based on this mapping, z is equal to e to the st. Let's look at the settling time. And this is the 1% settling time. Let's make the connection. The connection is via this mapping. And suppose now that I have two different locations. Maybe I have a green line and a blue line. Where the blue line, let's say, is corresponding to the dominant poles having a real part of magnitude sigma sub 2, and the green poles having a real part sigma sub 1. Now, how did we connect sigmas and r's before? We have r is equal to e to the minus sigma t. And we have a green and a blue sigma in this S-domain picture. So I have now one r, let's call it r1 in green, that's e to the minus sigma 1t. And we have a blue r sub 2, e to the minus sigma sub 2t. Now, which of these poles do you remember, or sets of poles, correspond to quicker settling time? Sigma 1 or sigma sub 2? 2. So we want to be further into the complex S-plane, left half plane, to be faster. Sigma sub 2 produces a faster response than sigma sub 1. How do we relate r sub 2 with r sub 1 in terms of value? If I now said r sub 2 blank r sub 1, where the blank is either greater than or equal or less than, which way is that inequality? Is r sub 2 less than r sub 1, or is r sub 2 bigger than r sub 1? R sub 2 less, let's say thumb down. R sub 2 bigger, thumb up. 1, 2, 3. Okay, it's down. So now we have this. R sub 2 is a smaller value. And what did r sub 2 and r sub 1 represent in the z-plane? That's the radius away from the origin. So that now I can actually plot these. Here is, let's say, r sub 2. which is this e to the minus sigma sub 2t, and you told me that r sub 2 was less than r sub 1, here is now r sub 1, which is e to the minus sigma 1t. And I hope now you see circles in the z-plane, or a bullseye. As we change the damping, we are going to, if we make the damping more, we're collapsing that circle. We have concentric circles, and those concentric circles are getting smaller as we improve or make the damping larger and make the system faster. The closer we get to the origin, the quicker that response will be. So now we have a bullseye, or a target, or concentric circles. And if we have a smaller circle, what does that mean about the system? Is it faster or slower? A smaller circle means a faster system. R sub 2 is less than R sub 1. So that now, when somebody says T settling, or the settling time in the z-plane, in discrete time setting, I want you to be thinking R, radius, or in terms of geometric shape, you now have a circle. And those circles need to be smaller for a faster system. So if you're playing darts, you're trying to hit the bullseye, you're trying to make that system really fast, you want to get as small of a circle as possible. Let's look at an example. Suppose somebody says we're given a settling time, T settle, and we want to know what is R. Again, what we're trying to do is we're trying to find desirable locations for our closed loop poles for a system. And in this case, we could, let's say, let T settle, some absolute time, be equal to some amount or number of sample periods. If we have a sampling period of capital T, then the settling time is some integer value of those sample periods. That's what we will use. Here, N sub S is the number of sample periods, and so I might play fast and loose. I might say the settling time is N sub S, or I may say the settling time is T sub settle. And T, just without any subscript, is our sample period. If we have this relationship between T settle and T, you could also think of this in terms of N sub S. If somebody says, oh, the T settling is 2 seconds and your settling period or your sample period is some value, you could determine how many sample periods it's going to be for you to have that 1% settling time. Or we just solve this T settle equal N sub S times T for N sub S, and we now have T settle divided by T. So, suppose that somebody says, oh, I want my state to be at 1% of where I started at time after so many sample periods, let's say capital N sub S. How do we relate that? If this is a one-dimensional system, if I just have one pole, that now says, oh, the dynamics will be influenced by that one pole's value R, raised to n sub s times the initial condition, x of 0. So the value of the state at time n sub s is r to the n sub s times x of 0. That's just for a one-dimensional, and that's how we will parameterize these settling times. We'll just find the value of the dominant pole, which means now the largest radius, and use that to determine our settling time. If this is now a 1% settling time, what do we want this final value to be? We want it to be 1% of where we started, which is 0.01 times x of 0. And if we now just focus on the right two equations in that expression, we can actually cancel the common x naught, and now it doesn't depend on the value of our initial condition. And we now can say that r raised to the n sub s is equal to 0.01. And this 0.01 is coming from our 1% settling time. And we're trying to now find relationships between the radius and the number of samples to get us to a 1% settling time. So now if you are outside the unit circle, we are not going to be having any kind of final value or settling time. So we really wouldn't be worrying about this settling time question if r is bigger than 1. So now we're assuming that r is less than 1 in magnitude to make the question have any meaning in terms of settling time. If we now take the natural log of both sides, and this is why it's convenient to look at a 1% settling time instead of a 2%, now we can find the, I'm sorry, not the natural log. Let's work with logs base 10 since we have a 0.01. So that now, if we look at this, we have n sub s times the log base 10 of r equaling the log base 10 of 0.01, or 10 to the minus 2, and logs are exponents, so we now have, that's why we like to look at 1%, because we can take the log of 10 to the minus 2 quite easily, instead of 10 to the some mess, or log of 0.02, base 10. Now we can solve this for log, or I'm sorry, for r or for n sub s, depending on how we want to do it. Suppose that we now look at log base 10 of r, that's now minus 2 over n sub s. And that formula now we can take either way. If we wanted to solve for r, we would do the inverse operation of base 10 log, which is now raise everything, or raise 10 to the each side of this formula, so that we now have r is equal to 10 to the minus 2 over n sub s. Meaning, if somebody says, I want a 1% settling time to correspond to 60 samples. After 60 samples, I want to be at 1% of where I started. We can now use n sub s of 60, and we now have r is equal to 10 raised to the minus 2 over 60, and that now becomes 0.926. So that now our pole, our dominant pole, has a value, a magnitude of 0.926, and that will give us a 1% settling time of 60 samples. And depending on what our sample period is, we would multiply that by n sub s to see the absolute time for what 60 samples corresponds to. What if we wanted to go in the other direction? Suppose somebody tells us the radius of our dominant pole. They're giving us R, and we want to now find how many samples it's going to take before we reach 1% of where we started. And now we can work with equation star. If somebody now gives us R, we can now solve this for n sub s. Or we can say now n sub s is equal to minus 2 over log base 10 of R. But n sub s needs to be an integer, so let me just go ahead and put that inside a function. And my brackets are created the way they are. This is my ceiling function. There's no basement on this. This is my ceiling function. Or that basically means that this is the least integer greater than or equal to the result of taking minus 2 and dividing that by log of R. And it's the least of those integers. Meaning, as an example, suppose that somebody says, oh, your dominant pole in your system has a radius of 0.8, or it's 0.8 away from the origin. You know it's stable. It has a magnitude less than 1. Now they want to know how many samples does that correspond to in terms of 1% settling time. And all we have to do is plug those numbers into that formula. The number of samples will now be minus 2 times the log base 10 of 0.8, which is now minus 0.09691, or that's now 20.64. And if we apply the ceiling function, how many samples does that represent? We want the least integer that's greater than or equal to 20.64. So now we want 21. It needs to be legal. Sorry. I lost my class 20 minutes ago, apparently. 21 sample periods. So now, if we're talking about settling time, what do I want you to see? When I say settling time, what are you seeing? What geometric shape? Circles. Now you're seeing a bullseye. You're seeing circles. So that now, when I say settling time, you should be thinking R's. What about percent overshoot? This is a different performance spec. But when I say percent overshoot, what are you thinking in terms of parameter? Omega sub n, zeta, sigma, omega sub d. What are you thinking of when I say percent overshoot? In the S domain, what were we thinking about? Zeta, the damping ratio. So now we have zeta, and zeta is related to percent overshoot by this formula that's now natural log squared of PO over 100 pi squared, which now you'll never forget what that is, right? Approximately 10 and you don't want to forget to take the square root of that result. what we want to do is figure out what the shapes are in the z-plane that correspond to these wedges in the s-plane. So let me try to walk through what that might look like. Here's the s-plane, and if I force a fixed zeta value, that gives me this angle, let's say theta. And for a given natural frequency, or if I fix zeta, I'm fixing that angle. Now I want to create many points in the s-plane. I'm going to vary the distance away from the origin on that angular line. So I'm going to be changing my natural frequency, omega sub n. Meaning I might have a natural frequency of omega sub n sub 1 right here, or omega sub n sub 2, or omega sub n sub 3. And now I want to see what that looks like in the z-plane. Cosine of theta was this real part over the hypotenuse, or theta now was the inverse cosine of zeta. And z, in terms of the parameterization that we've looked at already, is e to the st, or that's e to the minus zeta omega sub n, plus j omega sub n square root of 1 minus zeta squared times t, or that's e to the minus zeta omega sub n t, e to the j omega sub n t square root of 1 minus zeta squared. There's r, and this is e to the j theta sub d. And what do I want to do? I want to examine this parameterized form of z locations by fixing zeta. I want to fix zeta. Zeta is fixed in the r, and it's fixed in the theta sub d expression. T, I'm assuming, is fixed. The only thing that I can adjust is omega sub n, the natural frequency, and that's why I've indicated 3 different natural frequencies in the s-plane. What happens if I now have fixed zeta? What am I going to get relative to my r's? R1, let's say, is e to the minus sigma. Sigma is fixed. Omega sub n1 and t is fixed. I have r sub 2, e to the minus zeta, omega sub n sub 2 times t. R sub 3 is e to the minus zeta, omega sub n t. How are my r's related? How do I indicate the inequality? Is R3 greater than R2? Whoops. It's nothing unless I subscript that in. Here's zeta omega sub n sub 3 of t. And how did I have my omega sub n's related? Omega sub n1 was smaller, omega sub n2 was bigger, and omega sub n3 was the biggest. T and zeta are fixed. How is r sub 3 related to r sub 2? Omega sub n3 is bigger than omega sub n sub 2. So the exponent is a bigger value with a negative in front of it, right? So now this is R3 is less than R2 is less than R1. So as I march along that angle, that theta value, and increase my omega sub n, my radiuses, my circles are getting smaller, or the radius away from the origin. What about my angles? Theta d1 Omega sub n is what I'm varying. T is fixed and zeta is fixed. So that now theta d sub 1 is going to be omega sub n1 t square root of 1 minus zeta squared. Theta d sub 2, omega sub n sub 2t square root of 1 minus zeta squared, and theta sub d sub 3, omega sub n sub 3t square root of 1 minus zeta squared. Is it clear that this piece of all three of those is the same numerically? And now I'm simply changing my omegas. Again, I'm growing those as I increase from 1, 2 to 3. So that now, if I wanted to order my angles, which angle is the biggest? Theta D1 or theta D2 or theta D3? And keep going and keep walking up that angle. Which angle is the largest? 3. So now theta D1 is less than theta sub D sub 2 is less than theta sub D sub 3. So now for fixed zeta, what do I have? I have my r's getting smaller and my angles getting bigger as I march from 1 to 2 to 3. Is your head hurting yet? So my radius is getting smaller and my angle is getting bigger. I want to now map that in the z-plane for this particular dashed curve. What did I just say? My radius is getting smaller, so maybe for omega sub n sub 1, I'm here, and my angle is small. My angles are getting bigger, so now I have this one, and my radius is getting smaller, and then maybe I have this one. Good thing I did this in red. Because it's mirrored down here. Oh boy, that's... But do you see something just sort of pounding at you? It's not the best, but think Valentine's Day. That now looks kind of like a heart, does it not? And use your imagination. So now it's a heart on its side, and you can see that that was for a fixed zeta value. So a fixed zeta gives rise to these logarithmic spirals. And if I want more damping, what do I want my zeta to be? Bigger or smaller? I want zeta to be bigger. I want zeta to be growing or getting closer to 1. What do you think zeta equal to 0 gives me in this z-plane plot? Zeta equal to 0 gives me what shape? How does this heart distort when zeta is equal to 0? I have zeta equals 0 has how much damping? Zeta equals 0 is where in the S-plane? On the imaginary axis. It doesn't damp, does it? What was that? I don't know what that was. That was a frequency that never damped. Huh? I was on the imaginary axis. I was shaking. So now, when zeta is 1, we have a critical damp. When zeta is 0, we're not damping. What do we represent with no damping in the z-plane? The unit circle. Thank you. So zeta equal to 0. Oh boy. That's the unit circle. And as zeta is getting bigger, these logarithmic spirals start collapsing. Let's say that this is zeta equals 0. Let's say this is zeta equal 0.2, and let's say this is zeta equal 0.9. These logarithmic spirals, these hearts, are now collapsing on themselves, getting smaller. And what does that mean in terms of behavior of our transient? What did zeta correspond to? Percent overshoot. So if we want less overshoot, we want to be bringing our dominant poles to be next to these zeta values, these particular hearts. Now, what can we do? Now we can just play with this to our heart's content. Sorry, you guys aren't paying attention, so I'm going to have to entertain myself. Possibilities, or what happens if we start combining design specifications? For example, suppose that somebody says, oh, I have a settling time spec and I have a percent overshoot that's specified. Now you should be seeing shapes. When you say T settle, or when I say T settle, you think circles, R's, right? All right, don't say what you think, but play along. T settle leads to R. Percent overshoot. So this is now circles, or if we wanted to think of that, we've now, a settling time is now giving us something like that in the z-plane. Percent overshoot gives us what? What parameter for the percent overshoot? Natural frequency, damped frequency, sigma, zeta. Pardon? Okay, it gives us zeta, which gives us hearts. Good, so I need to do that in red, if my pens will cooperate. So now we should be seeing hearts. And we're not playing cards, we're actually seeing hearts. So now we have maybe these logarithmic spirals, and we want to know where are the pole locations. How do we find poles? Well, we need to find a z. And how do we find z? Well, give me an r, give me a theta sub d, and you have a z, right? I don't know, how do you do a z? You guys can show me after class. We don't have time to create z's. But we now say we're given an r from the t settling, and from the percent overshoot, we have a zeta. We now want a z delta, which is r e to the j theta sub d. Oh, great. How do we do that? I didn't give you a theta sub d. I gave you a zeta, and I gave you an r. But we can back that out. We can find a theta sub d. Here's how we're going to do it. So that now when somebody gives you an R and they give you a zeta, they've given you a T settle, they've given you a percent overshoot, you can now try to find the z-plane locations for R and theta sub d. We know R is equal to e to the minus zeta omega sub n t, where this is our sigma. Now, let's go ahead and take the natural log of both sides, since e is sitting in our equation, and we now have the natural log of r is minus zeta omega sub n t. Omega sub n t is floating around in a lot of different places in these formulas. Let's now solve for that. And that gives us now minus natural log of r over zeta. And now we have theta sub d. Theta sub d was omega sub dt, but omega sub d was omega sub n square root of 1 minus zeta squared times t, but that's now omega sub nt square root of 1 minus zeta squared, and voila, omega sub nt is minus natural log of r over zeta, so that we now have minus natural log of r over zeta times the square root of 1 minus zeta squared. And that is theta sub d. So you give me an r and a zeta. Now you can actually find the point z sub delta, which is r, e to the j theta sub d. Only about 30 slides behind where I wanted to be. I had too much dancing and too much. We'll stop at that point.